So let's think of a reaction engineering problem where we have a reaction, simple reaction A to B, and taking place in a CSTR, right. But here we are conducting the reaction adiabatically. That is Q dot equal to 0, right. So temperature is bound to change provided we have heat of reaction not equal to 0, right. So, so far we have discussed about the isothermal, the reaction operation or the reactor operation in isothermal paradigm. So, now we will think that if we operate a reactor adiabatically, which is more close to reality, what will happen and what problem we will face, right, and particularly from the perspective of design. Like here the problem is, what will be the volume of the reactor if we want a fractional conversion of say 0.7 or 0.8 and it is a constant volume system, right. So, if I try this, we know that we have tau by Ca naught equal to V by Fa naught equal to Xa by minus Ra or XAF at minus Ra at XAF, right. So, you have to calculate the volume. So, volume equal to Fa naught into XAF by K naught into e to the power minus E by RT into Ca naught into 1 minus XAF. So, here comes a problem because of this temperature, what we do not know, right. We may be given with an initial temperature like T naught or T initial, let us say it is 350 Kelvin, right, and the heat of reaction is also given, delta HRX is given. So, what problem we are facing? We know this XAF, we know Ca naught, right. This Arrhenius model is given, Fa naught is known, K naught is also known, we know this activation, this energy. However, we do not know temperature, right. So, if I do not know temperature, and temperature being a variable, because from the beginning the temperature, if this reaction is exothermic reaction, that is heat is being liberated in the system. So, under this condition, with the increase or with the progress, rather with the progress of the reaction, the temperature is supposed to increase, and just the reverse will happen if the reaction is endothermic. The temperature with increased conversion will decrease, and we know that conversion is going to increase with time and with the progress of this reaction from Xa to 0 to XAF equal to 0.7. So, if I have to find the volume, we must know a functional form, that temperature, how it is related to the conversion for this specific system. So, from here if we try to introspect, that we can understand what we need is an energy balance equation, right. What so far we have not studied, because so far we have considered that the system operates isothermally. So, fundamentally from this discussing about this problem, where we have a new paradigm, that is an adiabatic one, with a given temperature and with non-zero heat of reaction. What we have to point out that we need a general energy balance equation to deal with non-isothermal reactors, right. So, for non-isothermal reactor design, which is close to reality, non-isothermal reactor design, we need to have an energy balance equation. Right? And it must be a general energy balance such that we can extend this for non-adiabatic one also, where some heat is given or abstracted. So, we think of a reactor, right, it may be a general black box, right, it is a general black box, it may be having a stirrer or maybe a type of plug flow, etc. And here we restrict ourselves to the ideal reactors mostly, like batch mostly we will not discuss. We will discuss about these flow reactors like CSTR and PFR, because we don't know the non-ideal formalism which we are supposed to discuss maybe after 1 or 2 classes through this residence time distribution, that we don't know, right. So, for the time being, in undergrad courses, the course is designed in such a way so that we have an understanding of this energy balance mostly from the perspective of ideal flow reactors. Definitely it is extendable to non-ideal flow reactors, but that we are not going to discuss. So, let us say Q dot amount of heat is given to that system and the system is performing a shaft work of W dot S. Actually, this W dot S is negative if we have a stirrer, right. It is the shaft work, and W dot S is positive if work is produced by the system. Right? Now, let us say this flow rates, this is the molar flow rate of species I, right. Fi in, and here we have Fi out. And additionally, we have the energy Ei, right, in, and here it will be Ei out. Where E, you have to note that this is defined as sum of internal energy plus kinetic energy plus potential energy per unit, or actually it is to be converted to per unit mole. Okay. So, this is to be multiplied by the moles, not by mass, because we want the energy per unit mole, okay. Or rather, you know, this U square by 2 we can normalize with respect to these moles, right, because U square by 2 is the kinetic energy per unit mass. So, we multiply it by mass, right. So, you will get the kinetic energy. So, divided by the total number of moles, so you will get the specific molar kinetic energy. So, something like that, but actually it does not count because this U square by 2 and Gz, the kinetic energy and potential energy, these we will simply neglect in comparison to the internal energy for most of the systems. Okay. So, we can write that, thinking this as my control volume, simply we can write that d system dt is equal to Q dot minus W dot S plus sum of Fi Ei in I equal to 1 to n minus sum of Fi Ei out, then I equal to 1 to n. Right. So, this is the total work. It should not be the shaft work. It is the total work. Okay. Now, the total work is the total work produced by the system. Now, you see this total work, as we have discussed in fluid mechanics, it is the sum of shaft work plus work done by normal force plus work done by shear force, and that we set equal to 0 upon choosing the control surface to be always perpendicular to the direction of velocity. Right. So, shear work, as I am not discussing that, the shear work is set equal to 0. Now, what about the normal work? And here, this normal work, W dot normal, you know it was this integral with a minus sign sigma nn dA into V. Right, we have discussed it in fluid mechanics, and it is an integration over the control surface where sigma nn is a scalar component of the normal stress. So, this we have set it equal to P into V dot into dA, right, with a plus sign, as sigma nn is nearly equal to minus of P if the viscous effects are not very prominent, and we can justify it from the Stokes stress equation of fluid mechanics. So, with that, if I write this W dot normal, it becomes P into, or we can write P by rho into V into rho dot dA. Right. So, over the control surface, and this will be positive for outflow, as we know from this understanding of fluid mechanics, and negative for inflow. Now, without considering, if we don't consider the variation of this velocity and pressure over the sectional area of this flow port, that means if I have this area over this, the pressure is uniform pressure and velocity, right, we can reduce this integral into a summation without considering the variation of pressure, and velocity over the sectional area of the flow ports. We may restructure W dot normal as W dot normal equal to sum of this P by rho, it's basically P into V, right, and into this mass flow rate for all species I equal to 1 to n for out minus P into V into m dot, or rather we can write P is here, V is the molar volume, let's write, sorry, not the molar volume, that's the specific volume, that is volume per unit mass, right, and that is for outflow, and here P into m dot I for inflow, and there will be summation I equal to 1 to n. So it's basically pressure, right, pressure into the volume into mass flow rate. So specific volume into mass flow rate will give you the total volume flow rate, right. And here this Fi, they are molar flow rate. So you can replace, or we can further restructure this as P into Vi tilde into Fi for outflow minus P into Vi tilde into Fi for inflow, right, where Vi tilde is the partial molar volume. Of species I, right, because the partial molar volume into molar flow rate again gives you the total volume, okay, the total volume. So in this way we can actually rewrite this work done by normal force, and sometimes you must note that this is referred as flow work. So this work done by normal force, we have to note that it is also referred as flow work, right. So with that, if I now rewrite the equation once again, which is dE system dt is equal to q dot minus w dot s plus, sorry, w dot Fi ei in I equal to 1 to n minus Fi ei out I equal to 1 to n, and we write this as w dot s minus this one pi Vi tilde into Fi out minus plus pi Vi tilde into Fi in plus Fi ei in minus Fi ei out. So with that structure, this d system dt becomes q dot minus w dot s plus Fi ei plus p Vi tilde in minus Fi into ei plus p Vi tilde out I equal to 1 to n. And by definition, this ei, now we must discuss this capital Ui plus u square by 2 plus gz, and this we set equal to 0, and this must be the molar internal energy. Right. So if this is the molar internal energy of that system, so you see that what can be further what we can do it, this can be reduced to enthalpy, similar as this. So we can write that d system dt is equal to q dot minus w dot s plus fi hi in minus fi hi out. Right. So that's the typical energy balance equation we have also derived in case of fluid mechanics, but again I am rewriting it, doing it in a different way, not simply introducing the idea of Reynolds transport theorem and all. So we are doing it in a different way from this simple algebra. Okay. So generally what happens, let's not write this in and out repeatedly. Let's use the symbol 0 for inflow, and we can differentiate it. So d system dt is equal to q dot minus w dot s plus FIO HIO minus FIHI. Right, this is the typical outflow, and 0 associated symbol is the inflow. Okay. So definitely we can extend our analysis, whatever we are going to do, for unsteady state, but or mostly we try to simplify it initially. So we consider steady state analysis. Mostly we will be focusing on the design problem. Definitely we can go for simulation, but that will be a steady state simulation. So steady state consideration. So we definitely have d system dt equal to 0. Therefore, our equation reduces to 0 equal to q dot minus w dot s plus summation FIO HIO minus FIHI. I equal to 1 to n here, I equal to 1 to n here. So that's the steady state equation. Next we incorporate the reaction. Right. How we can incorporate the reaction? Through this enthalpy term. Definitely the heat of the reaction, the thermal effect of the reaction actually is expressed, or it affects the system, thermal state of the system through the liberated heat, right? And additionally with this enthalpy of these incoming and outgoing streams. So what we can do, let us consider a reaction with normalized stoichiometry There is A, the reaction is say AA plus BB giving CC plus DD. So what do we write? What is the normalized form? A plus B by A, B giving C by A, C plus D by A, D. Right. So now you see this summation Fi not Hi not. How we can write it? We can write it as Fa naught Ha naught plus Fb naught Hb naught plus Hc naught, Fc naught. There may be some converted product also, specifically in case of recycle streams, right. So, there will be some C and D as well. So, we have to keep the provision for that, and additionally we may have inert, right. And on the other hand, for outflow, FiHi is FaHa plus FbHb plus FcHc plus FdHd plus Fi into Hi. Now, Fi is same as Fi naught because it is inert. So, this is the inert term, inert material, a term for inert materials, right. Now, you see this Fi, we can write it as Fa naught into theta I plus this respective stoichiometric coefficient, right. The stoichiometric coefficient will be this let us say stoichiometric coefficient for I in normalized form multiplied by Xa. So, what does it mean? Like Fa we can write as Fa naught into 1 minus Xa, it is fine. Now, Fb we can write as Fb naught minus this B by A into Fa naught into Xa. Because if 1 mole of or Xa moles of A is converted, then the amount of conversion for B will be B by A into Xa according to the stoichiometry. So, that will be this Fa naught into Xa, right. So, here we can write further that Fb is equal to Fa naught into theta B plus or sorry minus here B by A into Xa, right. So, minus of B by A, so stoichiometric coefficient for B is equal to minus of B by A. So, next it is Fc will be equal to Fc naught plus C by A into Fa naught into Xa. So, you can write it as Fa naught into theta C plus C by A Xa. And similarly, Fd is equal to Fa naught theta D plus D by A into Xa. So, let us replace all this expression here. In the steady state design equation, and let us see what form it assumes. So, you see what you can write this the term was 0 equal to q dot minus w dot s plus Fi Hi or Fi naught Hi naught minus Fi Hi. So, I equal to 1 to n, I equal to 1 to n here. So, let us write this Fi naught Hi naught minus Fi Hi summation term first. Let us not include this q dot minus w dot s, let us first simplify this and then we will substitute it back. So, here it is Fa naught into Ha naught, Fb naught, Hb naught, Fc naught, Hc naught, Fd naught, Hd naught plus Fi naught, Hi naught. Now, minus Fa naught into 1 minus Xa into Ha minus Fa naught within bracket theta b plus theta b minus b by a Xa into Ha. For this term it will be Fa naught into theta c plus c by a into Xa into Hc minus Fa naught into theta d plus d by a Xa into Hd minus Fi naught into Hi. Right. So what you can write here, you see, Fa naught into Ha naught minus here Fa naught into Ha. Right. The first term, this and this. Similarly, theta b into Fa naught into Hb naught minus Hb plus theta c here for this term, theta c into Fa naught Hc naught minus Hc plus theta d into Fa naught within bracket Hd naught minus Hd plus theta I into Fa naught Hi naught minus Hi. And the remaining terms, if I group, what will happen? Yeah. So it will be minus, if I take common, d by a Hd, d by a, here we will have Hd plus c by a Hc minus b by a Hb minus Ha multiplied by Xa into Fa naught. Right. The inert term will not come here. And this is nothing but the heat of reaction. This entire first bracketed term is the heat of reaction at temperature T. So, finally, we can write this as theta I into Fa naught, the limiting reactant, into Hi naught minus Hi, right, minus delta H Rx into Fa naught into Xa. So that's the idea, and further we can write theta I into Fa naught into Cpi into Ti naught minus Ti minus delta H Rx into Fa naught into Xa. Now see, generally we pre-mix the reactant and whatever it is, it may be some recycle stream, we mix it and then feed it. So definitely we will not have different temperature for this different component, instead we will have a single temperature. Temperature of the different species is T, not Ti, because it is the common outlet temperature. Temperature of the different species at the inlet must be same. So with that, if I further simplify this equation, what we will get? So it is 0 equal to Q dot minus W dot S minus. So there is, here it is plus. Now you see, this is inlet minus outlet, and we have calculated, right. Yeah, we have calculated what? T minus T naught. So what you will get finally? Yeah. So this we can write as minus summation Fa naught theta I Cpi cap T minus T naught. There it was all Ti naught equal to T naught. So if we change the sign, so it is T minus T naught minus delta H Rx at T into Fa naught into Xa. Now we know from this thermodynamics that delta H Rx at T is equal to the standard heat of reaction at this reference temperature of 298.15 plus del Cp into T minus Tr. Right, where del Cp is equal to d by A Cpd plus C by A Cpc minus B by A Cpb minus Cpa. You solved it for. So finally our equation, the final form, would it become 0 equal to Q dot minus W dot S minus Fa naught theta I Cpi T minus T naught minus delta H Rx naught at Tr plus del Cp T minus Tr into Fa naught into Xa. So this is my working equation and you have to remember this. This is the general steady state energy balance equation for a reactor. Now let's again go back to that same problem we have started, with which we have started our discussion. Adiabatic CSTR. Right. And this Q dot equal to 0 and generally minus of W dot S or W dot S absolute value is negligibly smaller compared to Q dot. So, or this as it is adiabatic, this W dot S is also close to 0. Right. So, 0 equal to minus Fa naught into theta I Cpi cap T minus T naught minus this delta H Rx Tr plus del Cp T minus Tr whole bracket Fa naught into Xa. Right. And the reaction was A giving B, right? And there was no B in the inlet stream. So obviously we will have minus of Fa naught into Cpa into T minus T naught. And generally we can set this often this term is negligible. So definitely we can include that, but we can also set it as minus of delta H Rx naught at Tr into Fa naught into Xa. So Fa naught cancels out. So we have a straightforward relation T is equal to T naught plus this minus of delta H R x naught at TR divided by CPA into XA. So you see that this is a linear relation we have got and which expresses T as a function of XA. So XF in the previous problem was 0.7 or something like that. So you substitute, you get the temperature, replace the temperature in the design equation and you will get the volume. Okay? So with that, let's extend our discussion for what will be the case for general adiabatic reactor. So general idea, general adiabatic reactor. So what we will have here? We will have this 0 equal to minus Fa naught into Cpi theta I T minus T naught I equal to 1 to n minus delta H R x naught at TR plus del Cp into T minus TR whole bracket into Fa naught into Xa. Right? So Fa naught naturally cancels out and we have got Xa, what we obtained from energy balance. So let's write it as Xa EB. Okay. So that's equal to, we have the summation of theta I Cpi cap T minus T naught divided by minus delta H R x at TR plus del Cp T minus TR. Now as I have noted or as we have discussed that this term is negligible. Right. So we can safely write it as summation theta I Cpi T minus T naught divided by minus of delta HR naught at TR. So we are having a kind of linear relationship between Xa predicted by energy balance and temperature. Right. And it will be something like this. T here is equal to T naught. Right. So and its slope is summation of Cpi theta I divided by minus of delta HRx, and for an exothermic reaction it will definitely give you a positive slope. So that's the idea of adiabatic reactors. Now with that, let's try to solve a problem, or let's have a hint about a problem that how we can solve an adiabatic reactor, a problem of adiabatic reactor. So, what is the problem? Normal butane NC4H10 is to be isomerized to isobutane in a reactor, right, in a CSTR. Isobutane, why we have to do that? Isobutane is a valuable product that is used in the manufacture of gasoline additives. For example, isobutane can further react to form isooctane. The reaction, and isooctane, you know, it has got a direct linkage with this octane number. The reaction is to be carried out adiabatically in a liquid phase. Liquid phase means no volume change, under high pressure using essentially trace amount of liquid catalyst, which gives a specific reaction rate specific reaction rate of 31.1 hour inverse at 360. So, the K value, the rate constant value at a given temperature is prescribed. Calculate the CSTR volume necessary to produce 1633 kilomole per hour of isobutane, or 163 to necessary to process 163 kilomole per hour at 70% mixture of at 70% of a mixture of 90 mole percent N-butane and 10 mole percent I-pentane, which is considered as inert. The feed enters at 300 Kelvin. Right. So, additional information. So, what information is given? So, delta H Rx naught is equal to minus of 6900 joule per mole. Right. Activation energy of this reaction is 65.7 kilojoule per mole. Kc, the equilibrium constant, there is a reversible reaction 3.03 at 60 degrees Celsius. Ca naught is 9.3, yeah, it is Ca naught is initial concentration 9.3 kilomole per meter cube. Right. So, K1 rate constant 31.1 hour inverse at 360 Kelvin is given. And T naught is 330 Kelvin, the initial inlet temperature. Okay. So, additionally CPs are given, we will discuss it about, and Kc 40% conversion, and we have to go for a conversion of 40%, sorry, it was 40% of and 40% of a mixture, 90 mole percent N-butane and 10 mole percent I-pentane. So, initial fraction, mole fraction, X N-butane is 0.9, X I-pentane is 0.1, and CPs are given. Right, Cp for N-butane, I-pentane and I-butane, they are all given. So, what is the reaction? NC4H10, it is a reversible reaction, IC4H10. Okay. So, that is A, reversible arrow B. Now, we have V by Fa naught is equal to Xa by minus Ra. So, it is K into Ca naught into 1 minus, sorry, K into Ca naught. How we can write that? K into Ca, K1 into Ca minus K2 into Cb. So, Xa divided by K1 if we take common, within bracket it will be Ca into K2 by K1, and K1 by K2 is Kc. So, Cb divided by Kc. Right. So, this K1, see, K1 is equal to K10 into e to the power minus E by RT, E by RT, and one of the values is given, right. Say it is K1, let us say it is K1 prime. So, K1 prime is equal to K10 into e to the power minus E divided by RT prime. So, K1 we can write, if we have a ratio, K1 by K1 prime is equal to e to the power minus E by R within bracket 1 by T minus 1 by T prime. So, excluding this pre-exponential factor, we can write K1 is equal to K1 prime into e to the power minus E by R 1 by T minus 1 by T prime. So, that is our temperature and rate constant relation. Next, Kc. Kc is also dependent on this temperature, and that is Kc as a function of temperature. We have to generate it from Van 't Hoff isochord, whatever we have learned in this reaction equilibrium of thermodynamics. And that relation we can simplify as Kt or Kc into T double prime into exponential of del H Rx naught at Tr divided by R into 1 by T double prime minus 1 by T. So, that is the equilibrium constant thermal model. And stoichiometry gives you Ca equal to Ca naught into 1 minus Xa and Cb is equal to Ca naught into Xa. So, finally, what we will do? See, we have the reaction or design equation V by Fa naught is equal to Xa divided by K1. So, this is K1 prime into exponential of minus E by R into 1 by T minus 1 by T prime. That is fine. And here it is Ca minus or Ca naught into 1 minus Xa minus Cb naught into Xa divided by this Kc at T prime into exponential of delta H Rx naught by R 1 by T double prime minus 1 by T. This is T double prime. So, this is in general basically a function of Kc as a function of T, and this is, we can write this a known function of K, which is a function of T. So, V by Fa naught is equal to Xa divided by K as a function of T. Then we can take this Ca naught common, right? Sorry, this is Ca naught common, 1 minus Xa minus Xa divided by Kc as a function of T. And we can take this as 1 plus 1 divided by Kc as a function of T whole bracket into Xa. Right. Next, we have to consider the energy balance. So, it is Q dot minus W dot S 0 equal to minus summation Fa naught theta I Cpi cap into T minus Tr minus delta H Rx naught at Tr plus del Cp T minus Tr whole bracket Fa naught into Xa. So, from there you see Q dot adiabatic and this W dot is also negligible. So, this delta Cp is Cpb minus Cpa, and what is given in the problem statement that both the specific heat of Cpa, which is N-butane, and Cpb, which is N-pentane, both are 141 joule per mole per Kelvin. So, this reduces to 0 as Cpb and Cpa are same. So now it is 0 equal to minus Fa naught Cpa into, sorry, this T minus T0, T minus T naught minus Fa naught theta b, right, Cpb T minus T naught minus delta H Rx naught at Tr into Fa naught into Xa. So Fa naught cancels out everywhere, and we have this and inert is there, right, inert is there. So minus Fa naught into theta I Cpi T minus T naught. So inert is this pentane. Okay. So what we will have, this theta b is 0, but there is inert. So we have to do what? Fa naught is cancelling out. So or we can write this Cpa into T or Cpa plus theta I Cpi into T minus T naught is equal to minus of delta Hrx at Tr into Xa. So from the given value, this T can be expressed as a function of Xa, and if we substitute the values, we will get T equal to this 330, which is basically the inlet temperature, and this coefficient reduces to 43.4 into Xa. So what we have now, we have to go for a conversion of 40%, right. So if we substitute this Xa equal to 0.4, I can calculate T as it's coming to be this 347.3 Kelvin. So that temperature will substitute back here and here. So we'll get an Xa, we will substitute as 0.4, Ca naught we know, Fa naught we know, so we can find out the volume, right. So we can find out the volume, and my problem of design we can solve. So that's all for this adiabatic reactor and a basic analysis. So next we will think of this steady state, we will think of this PFR. We will not go for this typical adiabatic formalism, but rather we will approach generally that it is a non-isothermal, non-adiabatic case. We will derive the equation, and from there we will try to justify that what will be the respective equation for adiabatic PFR or tubular reactor. And similarly, we will also solve for the cases of non-isothermal, non-adiabatic CSTR. So that we will discuss in the next session. Thank you.